online.
Hello, everyone. Welcome to the seminar of the Astronomy Department of IAG-USP. Thank you all for your participation via Google Meet or YouTube. We are honored today with the presence of Dr. Patricia Tissera from Pontificia, Universidad Católica in Chile. Patricia Tissera is a professor at the Institute of Astrophysics and the Center for Astroengineering of the Pontificia Universidad Católica, and she leads the numerical formation and evolution of galaxies group at the Institute of Astrophysics and the Center of Astroengineering. Patricia completed her doctorate at the National University of Córdoba in Argentina, and she made postdoctoral stays at the University of Oxford, also in the Autonomous University of Madrid, and at the Imperial College. She's an expert in the study of physical processes that govern the formation and evolution of galaxies using numerical simulations. Professor Patricia, thank you for accepting this invitation. And today she will present the talk, Metallicity Abundances as Fingerprints of Galaxy Evolution. Questions can be asked to Patricia after her presentation. And if you are following the seminar through the YouTube channel, you can send your question using the chat. And before we start, I would like to ask all the colleagues to turn off your microphones and cameras during Patricia's presentation. And Patricia, please feel free to start.
Okay, thank you very much for the invitation. It's really nice to be here. Hopefully next time it will be in person in São Paulo. So I will talk today about this metallicity abundances as fingerprints of galaxy evolution. And just to start, to getting into the subject, what I do or what we want to do is to study how galaxies form and evolve from the first fluctuations or the small fluctuations in the distribution of the matter to the galaxy or the complex structures that we see today at redshift 0. And we want to understand how this process of galaxy formation or galaxy assembly proceeds, and what are not only what are the physical mechanisms playing a role at each redshift, but the different efficiencies that these mechanisms have, or the impact they have on different properties of galaxy. And many years ago, we started including in the numerical simulations chemical evolution, so the enrichment by different sources that provide us with a very powerful tool. Because now the galaxies that we simulate or that we use to study galaxy formation not only have to look as a galaxy or have the dynamics of the galaxy and the spatial distribution, but the stellar population and the interstellar medium should have chemical abundances that resemble or reproduce the observations. And these are very important information, and also very difficult to get. So I think it's real important. Not only it's important to understand how galaxy forms, but also it's important to set constraint on the physical models that we introduce in the simulations. So in general, the picture of galaxy formation include these elements, so these these physical processes, and when we use numerical simulations and hydrodynamical simulations, some of them are included from more physical motivated basis, and some of them have to be modeled in a more simplified with more simplified recipes. So as you can see in our models, we follow the growth of the structure, the collapsing, fall, and the mergers. And we also follow the gas cooling and the condensation of the baryons in form of gas in the center of the dark matter halos. And we also include recipes to transform the gas into stars. And we follow the stellar evolution. So we follow by assuming an initial mass function, we know how many supernova 2 we should have, how many supernova 1a should we have, and include the chemical sources of these elements that these stars can produce and eject into the interstellar medium. So when the stars end their life as supernova, they not only inject these chemical elements into the interstellar medium, but also inject a large amount of energy. And this energy, plus the chemical elements, also contribute to regulate the subsequent star formation activity, since this energy can heat up the gas and disrupt, for example, the cold gas where the stars, the cold clouds where the stars can form, and also the presence of chemical elements into the interstellar medium can change or will change the cooling times. So the fact that we can follow continuously the enrichment and the variation of the chemical abundances in the interstellar medium and hence in the stellar population that form from this interstellar medium, allow us to get this chemical information or the chemical relation between the dynamics and the chemical abundances of the interstellar medium. So in these numerical simulations, we also have the effects of the environment, which means that the effects of mergers, interactions, run pressure, I mean, they come out naturally because we're working within a cosmological framework. So all these elements are taken into account in the simulations, and the fact that we include the chemical abundances, we can study the chemical dynamical patterns. Okay? So we can identify and follow and study the galaxy with different morphology that where the gas component and the stellar population have different dynamical characteristics, and associate or relate them to their chemical abundances. In particular, during the last years, I have been focused a lot on the metallicity distribution in star-forming regions, and this is what we call the metallicity profiles, and these are observations from the SAMI survey, where you can see that for different galaxies, we have this metallicity distribution as a function of radius. In this case, it's the oxygen over hydrogen abundances as a function of radius. And we can see from this template that the set of plots that all galaxies have a clear metallicity profile, with the central region more enriched than the outer parts of the galaxy. But the slope of this metallicity profile change from galaxy to galaxy. So there should be, or what we expect is to have some information regarding how these galaxies form, encoded in the characteristic of the metallicity gradient, so the metallicity profiles. So we started many years ago studying these metallicity gradients, how they form in these galaxies. And we use numerical simulations, as I mentioned before. So we studied, and we know that if a galaxy forms inside out, it's a disk form inside out, because the star formation starts from the central and more dense gas, we will have more, the stellar population we have will be more enriched, and also the interstellar medium. And as we move to the outer part of the disk, you get less metal enrichment, or a stellar population with less abundances, lower abundances, and also the interstellar medium or the star-forming region will be lower abundances. And this is a scenario where a negative metallicity gradient is predicted, agreed with observation, and can be explained by this by the formation of the disk within an inside-out framework. So where normally you can have this when there is also angular momentum conservation. So the disk, when we run a cosmological simulation, we get this picture. We get the formation of the disk. We get a stellar population that are more enriched in the central region, that are older in the central region. And as we move to the outer part, we get less younger stellar population. And these stellar population are less enriched in the very outskirts. If we look at the interstellar medium, we get a similar trend. This is a profile, also oxygen over hydrogen of the disk component. So I'm not taking into account the bulge here. And we can see that the interstellar medium have this negative metallicity profile. And while the stellar population also have a negative metallicity profile, not always with the same slope. So we know from this previous analysis that if we form a disk by angular momentum conservation, it forms inside out, and then we will reproduce these negative metallicity gradients, and the regulation there are some processes that regulate the star formation, like the supernova feedback or the accretion of material, the smooth accretion of gas from the circumgalactic medium, could contribute to change the slope. Okay. However, we also know that in the cosmological framework, the current cosmological paradigm, the lambda colder matter scenario, galaxies formed by the aggregation of substructure, the halos, and within the halos, galaxies experience mergers and interaction with other galaxies. And these violent events also contribute to disturb the galaxy, change their morphology, and regulate the star formation activity, and also regulate the profiles of the metallicity profiles. So we carry out these mergers, control merger simulations, where we started from this galaxy with a certain metallicity profile, and we follow the evolution of the metallicity profile as a function of the redshift. So we can see that this metallicity, how these metallicity gradients change as the merger or the interaction proceeds. So there are physical processes like mergers and interaction, but also stellar migration, secular evolution, and gas inflows that can modulate this initial negative metallicity gradients and flatten them, break them so they have different slope as a different radial intervals, and also even invert it and make them positive. Okay. So, and we can see this in this picture, where we follow the evolution from the first pericenter, which is the blue lines. I mean, the starting of this merger interaction, this interaction of galaxy, and then how the metallicity profile, the metallicity gets lower as a function of time in the central region. And this is because gas from the outer part is transported into the central region, because the angular momentum is redistributed by the effects of the tidal torques. So part of this material lose angular momentum and fall from the outer part to the inner part and dilute the metallicity in the inner region. So this contributes to flatten the metallicity gradients. And also because there is part of the material from the interacting galaxy that is accreted by the other galaxy. Then we have material in the outer part of the disk that comes from the outer galaxy, and this will enrich the outer part. And also we have galactic fountains, material that is ejected from the inner part by the supernova winds and accreted in the outer part, and this material will be chemically enriched, and this produces also this change of profile in the outer part. So we can compare this evolution to an evolution of an isolated galaxy, and we can understand in this simple scenario how these different processes affect the distribution of chemical abundances. However, galaxies have different masses, and they evolve probably differently because of their different masses, as we know, and also they will be also affected by the environment where they are formed or where they live. So observationally, there has been quite a lot of work gathering the information on the metallicity gradients as a function of the mass of galaxy. And from the MAGNA survey, we can see that there is this kind of trend where there is, for galaxies larger than 10 to the 10 solar masses, we have an increasing positive metallicity gradient, in the sense that the metallicity gradients, which are negative, gets flatter, or they're shallower as we move to higher masses, but they also get shallower as we move to lower masses. So the processes that affect the high mass end might be different from the processes that affect the metallicity distribution in the lower mass end. For example, supernova feedback may affect this region more than this other, the high mass end, and the AGN activity will go the other way around. So in order to understand this, we can resort to the numerical simulation and try to analyze this. From the observational point of view, we also have information of the metallicity gradients as a function of radius. So we now have a compilation of information that will increase in the next years of the metallicity content from redshift 0, or the gradients, the metallicity gradients, towards higher redshift. And the general trend, I mean, the observations are the symbols here, is that there is an increase of metallicity gradients of what we call positive or inverted metallicity gradients. So metallicity gradients that show that the inner part of galaxies have lower metallicity than the outer part of the galaxy. Although there are negative metallicity gradients, some of them are quite shallow, but there is also seems to be an increase of these inverted metallicity gradients. You can see also that there is quite a large spread, large error bars. So it is quite difficult to get a good signal, a good determination of the metallicity gradient for higher redshift. So we need still to get more data, but as we get more data, it seems this picture seems to be reinforced. And here you have an observation from a paper from 2022, where again we have the metallicity gradient as a function of the stellar mass. And here is for high redshift galaxy, redshift that are about redshift 2. And here you can see that we have the same trend, even a little that reinforced or even stronger, so that more smaller galaxies tend to have these inverted metallicity gradients with larger frequency than a high mass galaxy. So we started to analyze this using now the Eagle simulation because it provides a large volume and we can have a larger statistic. So we measured the metallicity. We selected galaxy from this Eagle simulation. We used two simulations, the 100 megaparsec box and the 25 megaparsec box with a higher resolution. And we identify the galaxies, we measure the metallicity gradients and fit it a linear regression between 0.5 and 1 point effective radius, okay? And we make a statistic and try to analyze them statistically. So here, this is what we found at redshift 0 by analyzing the galaxies from the larger volume, the 100 megaparsec volume. Again, we have the metallicity gradient as a function of the stellar mass, and you can the symbols, the black symbols are observations, and the lines are the results from the simulations. So at first sight, you can see that the simulations reproduce or produce shallower metallicity gradient than the observations, and the trends are not so clear as the ones that are produced or are being observed. If we take the galaxies that are dominated by the disk, so they will be kind of spiral galaxies, the relation between gradients and mass are shown by this dashed line. We see a trend for the galaxy to have shallower metallicity gradients at higher mass, but with this simulation we cannot go to very low masses because of the resolution. So there is a small trend for galaxies around 10 to the 10 solar masses and slightly below 10 to the 10 to have more negative metallicity gradients than those that have larger masses, stellar masses, which is in agreement with observation. We also follow these galaxies back in time and found those that have important mergers or more significant mergers. And these galaxies tend to have a weaker relation, almost no relation with the mass. And the ones that didn't have mergers have a more clear trend between metallicity gradients and stellar mass. So these galaxies that have no mergers or no significant mergers also tend to be disk dominated. So if we take these dominated galaxies in this simulation, we reproduce a trend with mass, at least for the high mass end, that reproduce the observations. And the ones that have mergers normally are more bulge dominated, and they have a kind of a more flat relation with mass. And also an interesting trend that we found is that between the metallicity gradient and the scale. In this case, I'm plotting the inverse of the disk scale length. And the observational trend reported by Bresolin in 2019 is given by this line, which is shown in orange. And here we separate our galaxy, the Eagle galaxies, in two samples according to the sign of the metallicity gradients. So the galaxies that have negative metallicity gradients are shown by this shaded area and the lower blue line, and they agree very well with the relation, the trend between metallicity gradient and scale that we get from the observations. Okay. For comparison, also I include here the theoretical trend that we expect in a scenario where the disk formed by perfect angular momentum conservation in halos that have a spin and angular momentum of about 0.07. This was a model produced by Bransos and Bossier in 2000. And you can see that their model predicted a steeper relation that is not reproduced by observation and is not reproduced by the Eagle simulations. And we can understand this because simulations, galaxies do not form by following a perfect angular momentum conservation scenario, but there are processes like mergers that redistribute the angular momentum. So overall, we have this kind of overall angular momentum conservation, but not in detail. So the simulations agree with this scenario, but also we can see that the galaxies that have positive metallicity gradient or inverted metallicity gradient follow almost no relation. So the processes that affect the distribution of metallicity in these galaxies and produce the inversion of the metallicity gradient has nothing to do with the scenario of galaxy formation, and actually are quite violent. I have deleted almost any relation with the scale of the galaxy. We can also study the efficiency of the star formation process in these galaxies, in the ones that have positive or inverted metallicity gradient, positive or negative metallicity gradients, and the ones that have negative metallicity gradients are in blue, and in pink we show the distribution of the depletion time, so the star formation over the mass gas in the galaxy. We show this depletion time for massive galaxies and low mass galaxy and high mass galaxy, and those with positive and negative metallicity gradient. And you can see that the ones that have inverted or positive metallicity gradients tend to have a lower depletion time, which means that they are less actively forming a star for the gas fraction that they have, compared to the ones that have negative metallicity gradients. So one condition that we found in the simulations for galaxies to have these negative metallicity gradients is that they are currently actively forming a star across their disk. And those that have a more inverted or positive metallicity gradients currently they are not forming so actively star formation, are not actively forming, transforming their gas into a star, but did in the recent past. So we also measure these metallicity gradients as a function of radius and as a function of, redshift. So here is what we get from the Eagle simulation, but now using the high resolution box that they have. So this is a 25 megaparsec box, because we wanted to estimate the metallicity gradient up to redshift 2.5. And you can see that the line, the blue line shows the trend that we found in the simulation, that is almost very flat, a very weak evolution of about 0.02 dex per kiloparsec between redshift 2 and redshift 0. And the range of metallicity gradients that we found in the simulations the variety increased with redshift, So at higher redshift, we have a larger fraction of this inverted or positive metallicity gradient, which seems to agree with observations. So although they are within the observed range, which again are shown by these black symbols, and we found these trends that to have a slightly larger fraction of positive metallicity gradient with higher redshift, the simulation seems to produce metallicity gradients that are slightly too flat compared with the observation, but again within the observational range. We also studied the dependence of the metallicity gradients as a function of stellar mass as a function of redshift, and you can see that as we move from redshift 2 to redshift 0, in general the metallicity gradients get flatter. So the linear regression for the simulations are given here in red, at intermediate redshift in green, and at lower redshift in blue. And you can see that the slope gets flatter as we move to higher redshift. So the galaxies that have evolved strongly from redshift 2 are the small galaxies, which get flatter as we move to redshift 0, and the ones that evolve less are the more massive one, because they get to redshift 2 already at a more evolved stage of evolution. We also analyzed the time from the last merger to try to relate the sign of the merger, the fact that they have a metallicity positive and negative metallicity gradient, but also we went a little further and we divided the sample in a strong negative metallicity gradient and a strong positive metallicity gradient by adopting 0.02, which is approximately the median value. And then everything which is in between is what we will call it weak gradients, weak metallicity gradients. And we determine the time to the last major merger. So we plot the frequency of these strong, strong positive, and weak metallicity gradients as a function of the time to the last merger. And we also estimate the time of the last major increase of stellar mass of this galaxy by any process. We didn't. We put all processes that could contribute to the increase of the stellar mass by more than 25%, regardless of what it is. I mean, it could be a merger, a dry merger. It could be a wet merger that induce a strong starburst, or could be an inflow of gas from a filament that also increase the star formation activity. We are kind of agnostic about the mechanisms that produce this increase in star formation. We only try to relate this time of the last increase, the last main increase of stars in the galaxy with the shape or the gradient of the metallicity profile. So we divided this sample according to the mass. So we can see that low mass galaxies and intermediate mass galaxies tend to have positive metallicity gradients, or even strong metallicity gradients, if they have had a violent episode that increased strongly the stellar mass, and this episode could be related with a major merger, okay, because we found some trends with the time of the last merger. And in the case of the higher mass galaxies, they tend to have a stronger metallicity gradients, negative metallicity gradients, and this could be due to the fact that these galaxies have less gas fraction and they are more evolved. So, for example, mergers or gas inflows will not affect very much the distribution of material in the disk. They will be more stable, and we think that prevents gas inflows, but allow the material that comes from these events to settle into the disk in the outer part, producing an even stronger metallicity gradient, negative metallicity gradients. I'm not sure how I'm doing with the time, but I think I have several minutes.
It's fine.
Okay. So here we also analyze them as a function of their characteristic. okay, and as a function of the time to the last merger. This is a quite complicated set of plots, but we divided the galaxies according to mass, and then we divided them according to interval, redshift interval. So red would be high redshift galaxy, green intermediate galaxy, redshift galaxies, and the blue with the node relation for the more local or low redshift galaxy. And we can see first what we expect. I mean, the fraction of gas is higher at higher redshift, and the fraction of gas decrease with this galaxy as the stellar mass increase. And a similar relation with the specific star formation rate, and then we show also the morphology, which is the disk is measured by the disk to total mass ratio, and the depletion time. The vertical line here shows about 2.5 or 3 gigayears, which is the time to the last major merger. So this part, or this will be the galaxies that had a merger in the recent past. And we can see that in general, they tend to have a larger star formation activity, for example, that galaxies that have their last merger many gigayears ago. So we find a relation between the availability of gas in these galaxies, the fact that the galaxies that have a recent merger also tend to have larger fraction of gas, which means that these mergers sometimes bring gas to the galaxy and produce an increase of the star formation activity, disturb the morphology of the galaxy, because the ones that have recent mergers are more likely to have this low disk to total mass ratio, and they also have or show low depletion times. So we in this work, what we try to do is to make a link between the recent merger activity, or either by detecting the last merger, or by detecting the last episode that was responsible of a large increase in the stellar mass of the galaxy, and correlate that with the sign or the slope of the metallicity gradients. And we found that they agree. I mean, when you have a violent event, they follow the picture that we talked about at the beginning, that we got from the analysis of these simple merger experiments, where we put two galaxies, these galaxies to evolve, and we control every parameter in the simulation. We can see that these trends that we found can be reproduced in a cosmological context, although the signals are noisier, because we detect galaxies at different stages of evolution, and also we are restricted by the number of snapshots that we have to analyze this merger history of the galaxy. Okay, so in the cosmological simulation that we have used, which is CIELO, we only have 20 time steps where we can measure from redshift from very high redshift to redshift 0. So within redshift 0 and redshift 2, we only have about 10 snapshots where we can follow this evolution of the metallicity gradient and the property of the galaxy. So the signals that we get, or the results that we get, are noisier, but again, we can detect statistically the same kind of effect related with the accretion of material, either gas or mergers or major mergers. And the last thing, the analysis that we did in this Eagle simulation was to actually pick up galaxies at redshift 0.5, those that have, I'm going to focus only on the ones that have a strong negative metallicity, strong positive metallicity gradients, and a strong negative metallicity gradients, okay? So we pick those that have at redshift 0.5 these strong metallicity gradients, and follow them back in time, and either to higher redshift and to low redshift. So we studied the progenitor galaxies at redshift 1 and the descendant galaxies at redshift 0.1 to see how these metallicity gradients change with time for a given galaxy. Okay, so this is not only a statistical analysis, but each of the galaxies that we pick up here at redshift 0.5, where we found their progenitor and their descendant. And what we found is that the galaxies that have strong negative metallicity gradients, for example, are at redshift 1 more disk dominated, which is shown by this line here. This is the disk to total ratio. This is the median. So they have 0.46 median disk to total mass, while those that have strong positive metallicity gradient at redshift 1 are more spheroidal dominated with a median of 0.2 in disk to total ratio. As they evolve in time, they get slightly more disk dominated, but the ones that have negative metallicity gradients evolve strongly, and they conserve their disk morphology, and even at high redshift, some of them are still they have a strong metallicity gradients. But we also detect that some of them, in general, they get flatter, they get shallower, so, and even slightly positive for some of them. So, so what we found in general is that a galaxy that have a negative metallicity gradient, if it is a strong one and a clear one, are disk-dominated galaxy, and they can be disturbed as they evolve to lower redshift. And they or this perturbation can make them make their metallicity gradients slightly positive or very shallow, but also the continuous transformation of gas into a star produce the same effect. So they get shallower as a function of time as we move to lower redshift. In the case of the galaxies that were found to have positive metallicity gradient at redshift 2.5, as I said, when we found their progenitors at redshift 2, they have a spread of metallicity gradients, but they are more disk dominated and they are smaller in size also. Here we have the effective radio, and the median effective radio is 1.5 approximately. And they grow as we move to lower redshift as expected, but they continue to be mostly to have inverted or positive metallicity gradients. So this picture or this story tells us that in the case of the galaxies that have positive metallicity gradients, it's a little more difficult for them to recover after they got this very strong metallicity gradient, but some of them do by accretion of material and by forming stars again in the central region, and they end up having this kind of a weak negative metallicity slope. But we found that in this Eagle simulation, there is an important fraction of galaxies that remain with the positive metallicity gradient even to redshift 0, which is something that has to be, I think, still confronted with observations to see or to set constraint on the subgrid models, because if there is an excess of this galaxy that have inverted metallicity gradient at redshift 0, that means that the subgrid physics should be revised in order to solve the problem. But there are not, I think, enough study of the frequency of positive metallicity gradient at redshift 0 still. So because, as you see, this is kind of noisy and it's kind of difficult to get a clean picture of how these metallicity gradients are evolving, we decided to go and run our own simulations. In this case, we ran zoom-in simulations of different galaxies with different masses in different environments. And we did that by using our own code. and we this code allows us also, I mean, this simulation allows us to have more snapshots to follow the evolution in time and to study how the galaxies interact with their surrounding environment, with other galaxies, or with the intergroup medium. So now we are studying in detail the metallicity gradients as a function of redshift, but for some cases, okay, but with much more resolution in time. So here you can see two examples of these galaxies that we got from these CIELO simulations. Both of them are this galaxy, this dominating galaxy, but they have they both have negative metallicity profiles. And you can see that we can reproduce them in this case by two power laws. And the outer part in this case is in this galaxy is broken. So as we saw in our first simulations. But in the other case, this galaxy, although we can fit some broken power law, it is better reproduced by a single profile. So we can do this kind of analysis for the simulations now, for each galaxy in our simulation, and plot these metallicity gradients as a function of time. And we can detect if there is a break, inner break. So if the galaxy have a flatter or a steeper metallicity gradient in the inner part, or if I mean, if the metallicity gradient can be described by one single power law, by two power law, or by three power law, okay? And we have a method to fit the combinations that better reproduce the metallicity gradients. So here you can see that the three metallicity gradients as a function of time, the metallicity gradient in the three regions, if it is possible to fit three regions. Otherwise, there are two regions in general. So the cyan shows the metallicity gradient in the inner part, the most inner part of the galaxy. The black line shows the metallicity gradient in the middle region, and the outer part is shown. The outer metallicity gradient is shown in pink. And this is preliminary results because we are working on this. But now we can follow in much detail what happened with these metallicity gradients. What happened with the oxygen level as a function of time. I mean, the level of abundance of this, the enrichment of the galaxy in the different regions, in the inner, middle, and the outer part of the galaxy. And we can also follow the star formation activity in each of these regions, and we can compare or confront the evolution of these properties with, for example, the merger activity. So this is the orbit of a merger that will happen about redshift 2. So we look back time, sorry, 2 giga years ago. Sorry, I'm starting to be tired. And we can, the idea is to now make a very detailed analysis of how the metals are distributed and which processes affect, if it is a merger, if it is an interaction with a nearby system. This is the distance to the satellite system that surround the galaxies as a function of time, or if there is accretion of gas. So this is the accretion rate as a function of the look-back time from gas that comes from the outer part, the unbound gas, which is the solid line, and from other galaxies or from the same galaxy. So the idea is to have a comprehensive study of the processes that affect the distribution of metals and what are the signals or what are the characteristics of the metallicity profiles that can be then associated to these different processes. Also, we can study the effects of the environment in this galaxy, because we can follow the orbits. So this is the orbit of a satellite that gets into the virial radio of a central galaxy, which is at the 0, 0. And we can follow how the material is disrupted as the system falls in and orbit around the galaxy. I'm not going to get into detail because I'm already, I think, over my time, but we can follow the orbits of these galaxies, and we can follow the star formation activity, the impact of the ramp pressure on the galaxy, and the torques that are produced by the nearby environment. And to finish, we are also using this CIELO simulation to mimic IFU observations, so we can pass from the simulated distribution of information. I mean, stellar particles in this case, a stellar population. We have the stellar population, their mass, their age, and chemical abundances, and we can produce an IFU from this simulated galaxy. And for each spaxel, we now have the spectral distribution. And we pretend, or we aim to have an observe, to mimic observation in such a way that we can study the local, the resolved local properties of the galaxy and compare with the global distribution of properties. And we are also studying how this material, the gas, is accreted in the galaxy, which gas is accreted aligned with the angular momentum, the main axis of rotation of the galaxy, and which gas or satellites are accreted counter-rotating, and what is the effect that this has in the distribution of the stellar population, the interstellar medium, and the metallicity and the chemical abundances of the objects. So to finish, for now several years, we have been working on trying to understand not only how these metallicity gradients or negative metallicity gradients are produced, but mainly how they are disturbed. What are the processes that regulate the shape of this metallicity gradient, and how can we associate this the evolution of the shape with the evolution of their evolution? I mean, how the galaxy is assembled. And so far we understand that what are the processes, the physical processes that affect the galaxies as a function of time, but we want to go a little further and have a quantification of their efficiency as a function of time and the impact they have in the distribution of on the global properties of the galaxies. Well, I think I am done. Thank you very much.
Thank you a lot, Patricia, for this very rich talk. It's a lot very interesting information, and especially thanks for showing these very new results from your ongoing research. We will now open for questions for Patricia. Let me see, we have 2 hands up. First, Laerte.
Hi, Patricia. Congratulations. Hi. Very nice work.
Thank you.
Well, I have many questions, but I will just ask one because you have shown that the properties of the metallicity of the gas phase, okay? This is the oxygen abundance that is inferred from the gas phase. In your simulations, you have also access to the stellar component. And I wonder how this variation in profiles that we see in the gas phase translates into the stellar population. I don't know whether you have looked at it, but I suspect that we may have interesting clues, because first we expect correlation, but the time scale of the response in different in the stellar and gaseous population are probably very different. I mean, in a merger, for example. So maybe this could bring new information. What could you say about it?
Yes, actually, we study, we have 2 papers in preparation. One is to studying the young stellar population, which we will expect them to have a metallicity profile which is closer to the interstellar medium. but what we found, at least in the Eagle simulation, I haven't done that with the CIELO simulations, but with the Eagle simulation, we found a variety of situations. Some of the galaxies have, let's say, negative metallicity gradients, because they have also very different slopes. But at least they have the same the signal. The gradient is in the same direction. But some of them are also negative and positive, or positive and negative, and some others are both positive metallicity gradients. So there is a large variety when you compare the metallicity gradients of the interstellar medium, which are star-forming regions in this case, and the young stellar population. So we are analyzing that to see if we can find some trends that help us to understand when or what are the time scales associated to these processes, or why they follow these different trends. And also we have studied the metallicity gradients of the whole stellar population and the age gradients. And we found also very very messy trends, but in this case, Rubens Machado is working in studying the metallicity gradients of the stellar population, and he found a very interesting relation with the ages more than the metallicity gradients. It seems that at least in the Eagle simulation, the ages, the gradients of the age populations show some trend with the stellar mass and with the morphology of the galaxy that are comparable with observations. But I cannot say much about the relation between the interstellar medium and the stellar population, because we are working on that.
Okay.
So maybe it would be better to use this Eagle simulation, the CIELO simulation, because we have more resolution and we can see the changes in time scale with more precision. So maybe maybe by the end of the year we have an answer. But yes, I think it's very, very interesting.
Thank you, Patricia.
Now we have a question by Elizabeth.
Hi, Patricia. How are you doing? Sorry, I got this flu, this cough, so it's very hard to speak. But very, very, very interesting talk. Very, very nice overview that you made. And actually, I have several technical questions and also physical questions. So since I do not have much time, I will go directly to the physical questions. So, of course, you are trying to get a major picture for star formation rate and metallicity ingredient correlations, right? Because at the end, this is what we want to understand. What is the star formation rate in these galaxies, and the integrated star formation rate contributions in galaxy clusters across the redshifts, right? And this is one issue that I'm very much interested, because recently we have been performing simulations of combining cosmological simulations with cosmic ray propagation in galaxy clusters across cosmological times, in order to derive the integrated gamma ray flux and the neutrino flux from these environments. And there is actually an observed correlation between these fluxes and star formation rate, because we might expect that these massive star forming regions will be the sites of production of high energy cosmic rays that in turn will produce this high energy emission and neutrino and so on and so forth. But in these cosmological simulations, in order to get the influence of feedback of star formation, of the evolution of the sources of cosmic rays, star forming galaxies and the AGN feedback, we had to assume some profiles, because those MAGD cosmological simulations that we employed gadget MAGD simulations did not account for these effects. And what we found is that indeed the star formation, these star formation rate and profiles, evolution across the redshifts do have an influence on the integrated fluxes of these emissions, neutrinos and gamma rays. And they can influence by a factor of at least 3, 10, up to 10 times when you compare with when you do not account for star formation rate evolution in these systems. So my question goes in this way. In your opinion, how these more, let's say, more precise or high resolution hydro simulations that you are doing in order to get isolate contributions from metallicity and star forming rates from individual classes, from the individual galaxies, and then at the end, eventually we may integrate all these contributions in order to get contributions from entire galaxy clusters. What is your feeling towards effects like the presence of magnetic fields in this parametrization, and if you had the chance to compare the results that you get from these simulations, localized simulations, with integrated star forming rate contributions from entire clusters at different redshifts. Did you have the chance to compare with these predicted profiles that come indirectly from simulations and from cosmological simulations, larger scale cosmological simulations? So I don't know if you understood my point.
I think, or at least partially, you can correct me. So one thing that I should clarify is that these simulations that we are running in the CIELO simulations do not include very high density regions. So we don't have clusters. The largest one is the local group size, mass size.
Right.
So we cannot compare with higher density environments. And I have not made these comparisons. What we are now studying with this local group galaxies is how this material that is disrupted from the two things: how the material is disrupted and what is the effect on the star formation activity of the satellites and the metallicity distribution. So I didn't understand quite well if you are including a profile for each galaxy. So if you care about the way how the star formation is distributed inside the galaxy, or just an average of the...
Yeah, actually it's integrated over galaxies, and then you have this over clusters of galaxies of different masses as well, across, and this as a function of shifts, right? So yeah, these integrated profiles actually are derived directly from simulations, cosmological, both cosmological simulations and from observations. Of course, this is very crude still, and the fact that you have some important feedback from these local simulations where you are studying chemical evolution, and therefore this correlation of a specific, as a function of mass of galaxies from individual galaxies, in spite of the fact that they can probe only local groups or small clusters, let's say small groups of galaxies. At the end, you do have a trend that can provide information on star formation rate integrated over these galaxies in a mass range, right? In typical mass range, because at the end you have all classes of galaxies, spheroidal, disk-like starbursts, and right. So in this sense, this might probe the entire population or typical population of the individual galaxies, which in turn populate entire clusters, and then this should reflect in feedback and star formation rate, etc., from integrated contribution. But yes, there is a gap between these two scales, and so I understand that this is rather complex, and
it's yeah, I haven't actually thought about that because of the environment. I mean, we were more looking at the individual processes that affect the galaxies so far. But there is a project, maybe not for the maybe for next year, to include also more massive clusters. But this is it's a compromise between power, computational power, and what we can do. So I think it's quite interesting because it's a different way also to check if these global constraints are also, I mean, if we can reproduce not only in detail what is going on inside the galaxy, but as a population, if we can reproduce like these global trends that you are talking as a function of the environment, I will guess. But we are not yet there, I think.
Yeah, but anyways, this gap between the two, eventually can be filled, and I think this information will be rather important for the largest case. Thanks a lot.
Yeah, thank you.
Patricia, I myself, I was very curious about one simulation, one study you showed your performance about the merger of two galaxies about 3 slides ago, and where you characterized the metallicity profile by 1 or 2 power laws. Yes. So I was just curious, because these characterizations by 2 power laws, this level of details, I mean, the outskirts, is there a robust fitting, or could it be just statistical?
In this case, there are very few particles. So we did is we have an algorithm that can fit this power law and use some statistical criteria to say if this is a real break, or if it is something that is spurious or is very noisy and can be discarded. So I think this is what I'm showing you. Maybe it's a slight old picture, because we have improved quite a lot, and actually we have you can see 2 lines there, because we tested with two models. One is for example has only two breaks, and the other one has 3 breaks. And sometimes even the worst is the inner region, because the inner region can fluctuate a lot, and there are more noise. In the outer part, when there is a break, normally you can, because we have a lot of time step, we can see if the break is stable over some slight short period of time. It's not something that you find in one step and the other step you have a different profile. So actually Brian, he did quite a lot of work in looking at them and see step by step visually, and doing the fitting of the algorithm to find that we are having something which is stable. We also do a lot of bootstraps to estimate the statistical sign that we get from these breaks. But the idea will be to go to a higher resolution simulation. So we have a higher, this is 10 to the 5 solar masses in resolution in baryons, and now we have 10 to the 4, and in the 10 to the 4 we have a similar trends. I mean, consistent with results.
Oh, can I make a related question to this diagram?
Yeah,
because it's very interesting, because it's a source of information that can give provides some insights about this, how these gradients modify with evolution.
Actually we are, I mean, I'm showing you just the preliminary ones, but we have a better plots or improved plots where we can see how the material moves from one region to the other, from the inner to the outer part of the galaxy in both directions, and along the z-axis in the case that we have outflows, for example. And we are studying the accretion or the rates of how they move. I mean, the fraction that moves, the metallicity, and metallicity and something else. And I think the temperature of the gas that moves. So we can quantify the origin and also the properties of this material that falls into. So I think it will be a really very good, interesting work when we finish writing the paper.
Yes.
Yeah.
So sorry, Beth, I interrupted you.
But Betty?
Maybe that is not following anymore. Oh, so if please, Beth, please go ahead.
Can I make a short question related to this diagram? All these points are related to a single simulation. All these points that are filling out this diagram, these black points, what they are exactly?
Yeah, they are gas particles that are in condition of forming a star. So this will be the star forming regions of the disk.
Right.
Of stars that are gas that is in the disk. So
right.
These are gas particles in the disk which are in condition of forming stars.
Right. So I suppose that the radius at which the broken power law occurs will change if you change the setup of this galaxy, right?
Well, these are cosmological simulations, so they actually will they do change. We can follow the break, where the break, the outer break is almost present everywhere, so we can follow in time and see how this break, where it happened in comparison, for example, with half mass radius of the galaxy. Yeah.
Right. Okay. Thanks.
So this is also something quite interesting that we are trying to see if there is. I mean, we can get some information from where this occurs.
Right. Okay. Thanks.
Okay, I would like to thank you again, Patricia, for sharing with us your work and for this very nice talk. And we can finish the broadcast now in YouTube. And I hope you can soon come presentially to give a talk in IAG again.
Thank you very much for the invitation, and I am looking forward to visit IAG and Sao Paulo in general. Yeah, Brazil. So let's hope.
Yes.
Let's hope for better times.
For better times, yes.
That's indeed. Okay.
Yes. Thank you. Okay. Richard, we can finish the broadcast.
Just a second. Can I just remember everybody that next week the seminar was canceled? Actually, it was postponed, but we won't have any seminar next week. So.
Good point, Larissa. Thank you.
Thank you.
Yes.
Bye, Guy. Thanks a lot.
Okay, bye-bye. Thank you.
Nice to talk to you again. Bye-bye.
Bye.
Many thanks, Patricia.